Swayam Prabha, free DTH channel for education.
Hello everyone, welcome back to the online video lectures of the medical imaging course. In this video, let us continue our discussion about image enhancements in the spatial domain. More specifically, in this video, let's start discussing about the spatial filtering. Let's move on to the notebook mode for working out more details about spatial filtering. Let us begin our discussion about image enhancement using spatial filtering with the help of some examples. To begin with, we will consider examples related to image smoothing in particular. Let's also draw a sample image here. Let this be x and this be y coordinates. Let each of those rectangular boxes represent each pixel. Let's call the image as I of x comma y. What we would like to do here is image smoothing. Let's consider some pixel here. We'll make few assumptions in order to perform the image smoothing. We obtain the smoothing by taking average of the pixels which are there in the neighborhood of that pixel of our interest. Assume that we are going to perform image smoothing, and as a result the new image, let's call it as in of xy, which is a smoothed image. Let's focus on this pixel. Assume that we are looking in a 3 by 3 neighborhood of that pixel. You want to take average of all those pixels. Assume here 3 by 3 neighborhood for performing image smoothing. How do we do it now? I of x comma y will be equal to, so we are considering a 3 by 3 neighborhood here. The whole we are going to consider 9 pixels here, which are I of x comma y plus I of x minus 1 comma y, so that would be this pixel, plus I of x plus 1 comma y, that would give you this pixel, plus I of x comma y plus 1, that would be this pixel, plus I of x comma y minus 1, which would be this pixel, plus I of x minus 1 and y minus 1, that one, plus I of same value of x but now go to y plus 1, that would be this pixel, plus I of x plus 1 comma y minus 1, giving you this, plus I of x plus 1 comma y minus 1. So that would be this pixel. Is there a better way to write these equations so that later we could generalize them to any width of neighborhood? Assume that the window size be w by w, and then also assume that w is an odd number here, which means you would be looking symmetrically around that pixel on the left, right, as well as top and bottom. Another notation for our convenience we are going to use is, when we are saying w by 2, it's in fact the floor value. For example, if w equal to 3, that implies we consider w by 2 as 3 by 2 1.5, but we consider it as 1 here. This is just for our notational convenience. We will be skipping this floor notation. Now let's try to write this earlier expression in the form of summation. How can I write that? I want the new value that needs to be replaced at the location indexed by x comma y is equal to, I need to change both in rows and columns. Use one index of I for row. This would be varying from minus w by 2 to plus w by 2. Then columns also I would like to change from minus w by 2 to plus w by 2. Then what will be there inside this summation? We are going to sum up all values associated with I of x plus I comma y plus j. Is that all? What is it that we are missing here compared to the previous expression? The multiplication factor of 1 by 9 is missing. Suppose if I am using 3 by 3 window, I am taking an average over 9 pixels. 5 by 5 window, average over 25 pixels. So this has to be multiplied with 1 by w square. Of course, I could take that factor outside. I want to generalize this a bit, where instead of doing a direct manipulation on I would like to use some other operator which we would be later referring to as a mask or kernel, where the corresponding values would be multiplied. So I would like to use a mask. Let me call for the time being it as mask of size w by w. By that I mean w rows and w columns. Let me call this as h now. Again, you consider this as symmetric, this being your center, and then of course the coordinates could be, if you want me to put the coordinates, this is how the coordinates of this are. Now I could represent the values as h of, let's say, I comma j. Now I would like to rewrite it in terms of h of ij. Now my in of xy, I could write it as I varying from minus w by 2 to plus w by 2, j varying from minus w by 2 to plus w by 2, I of x plus I comma y plus j multiplied with h of I comma j. Hope it is clear. Can you now tell me, for the above example, what would be the value of my h? H is equal to 1 by 9 into all values of this 3 by 3 matrix, this being the center, is 1 by 9, 1, 1, 1. So I am generalizing it so that later I am going to use different types of masks. Hope it is clear on how I moved the set of operations we are doing into the formulation of a mask indicated by h. By the way, have you seen this expression anytime earlier? I of n comma of x comma y being equal to I varying over a range of values. Similarly, j varying over another set of values. I of x plus I comma y plus j and h multiplied by I comma j. This is nothing but correlation. This operation is correlation. Before going further, just let me take one more example. Suppose I want to do weighted averaging here. If you notice in the earlier averaging example, all the pixels are contributing equally over the entire neighborhood. Suppose now I want to give, while computing the new pixel value, whichever is there at the center would like to give more weight to the pixel value indicated by that. Immediate neighbors are 4 neighbors we call, right? This and this are immediate neighbors to it. These are the diagonal neighbors. For example, this are the diagonal neighbors. So less weight to the diagonal elements, a bit more. I would like to reduce it. So for example, how could I write that? Since you know that a bit already from your signals and systems, I'm directly going to write it here. Least weight, let me write first. I want to give least weight to the diagonal elements. So I start there with 1. Then the diagonal elements more weight to the immediate neighbors. So let me give 2, 2. Even more weight to the center. So let me give 4. Now what's the whole sum? 16. Again, I want, you would like to normalize the whole thing. So you would multiply it 1 by 16. This is a one way of weighted average. We have empirically designed this weighted average kernel. if you want to do image smoothing using weighted average, this is one empirically done. For example, you could in fact use Gaussian based weighted averaging also. So in that case, you all know the 2D Gaussian, right? G sigma of x comma y is equal to 1 by 2 pi with variance being sigma square and exponential of minus of x square plus y square by 2 sigma square. Notice that the moment you are using a discretized kernel like this, you need to do something on top of the actual Gaussian curve, right? So that's where you have two parameters now if you are doing a discretized version of a Gaussian kernel, right? One is sigma value and another is kernel size, which is W here. So kernel size, which we are referring here by W. So based on that, you will be coming up with a kernel for where you use Gaussian based weights for designing your mask for doing the smoothing operation. So for example, here this whole thing could be contributing to the one kernel value, and then something like that you would be doing here depending on number of. So this 1 2 3 4 5, suppose if you are using 5 by 5 kernel, of course I have just drawn it in the 1D, so you could similarly think the values in the 2D case. Hope it is clear. Now let me come back here to the point that this is a correlation result. So essentially what you are doing here, you are correlating the input image with the mask in order to obtain the enhanced image. What we refer as enhanced image is a smoothed image, for example. Later we could use different masks for different other operations of enhancements. For example, where you would like to use edge enhancement, you will see different values for h of I comma j. Since you know another function similar to correlation from your DSP background, so what is that function which has certain similarities with correlation? It is convolution. Suppose if I want to perform a convolution here with a given mask, so how do you write that? Let's say I would like to convolve the given input image I of xy with some given mask h of I comma j. So how do you write a convolution operation? Let's call that resulting image. Let me call this as I2 of xy. How do I write that? Assume here that your h is of size w by w. So you would then change this from minus w by 2 to w by 2, again taking floor value. J is again varying from minus w by 2 to w by 2. I of x minus I y minus j multiplied with h of I comma j. So in a way, x comma y being the center, I am flipping that there, right? You already know from your DSP background that convolution operation satisfies commutative property. So if I want, instead of flipping the image for the point around x comma y, I could instead flip my kernel itself. So how could I write that? Then this expression would be I varying from minus w by 2 to plus w by 2, j varying from minus w by 2 to plus w by 2, multiply I of x plus I comma y plus j with h of minus I and minus j. So you are flipping your image in that particular region, right? Now compare this with the correlation operation here. Let me use subscript 1 here for correlation and 2 for convolution. So let me call this for consistency as I1 of xy. So how can I relate correlation and convolution? Suppose if I am going to flip the kernel that I am using for convolution, right, And with that flipped kernel, if I am doing correlation, that's exactly equal into performing convolution with the original kernel, right? Only this flipping of the kernel is what is the difference that is there between the convolution and correlation. So what I can say here, so convolution operation is equivalent to performing correlation with a flipped mask, right? Now, what you would observe as we go on this course for the next couple of lectures, that most of these masks are symmetric around its center. So let's see now what would happen if the mask is symmetric. What do we mean by mask being symmetric? That in fact means for any value of I and j, your h of ij is equal to h of minus I and minus j. In other words, flipping will give you the same mask, right? So that means, of course, then there is no need to flip it, because anyway you would get the same thing. Or in other words, you could say convolution and correlation would give you the same results. Since in your DSP you mostly dealt with the convolution of 1D signals, so let us take an example of flipping a 2D mask. So let's say my mask is 1, 2, 3, 4, 5, 6, 7, 8, 9. This being the center. This is your h of I comma j. Compute h of minus I comma minus j. That's what you need to compute. So one way is take each element here, and for that you do a horizontal flip. Okay, a horizontal flip, how do you do? Then you would be using this symmetry axis, and then you do the flip, and then you do for that particular element vertical flip. So that means you would be using this as your axis. But instead, one thing that you might find very convenient is you do a horizontal flip for the entire matrix. So you do a horizontal flip here, so that means you use this. So this top row becomes the bottom row becomes the top row. The elements which are there in the middle row would remain there itself. So what is it going to give you? Middle row remains there itself, that means 4, 5, 6. Top row becomes the bottom row here, that means this would become 1, 2, 3, and this bottom row would become top row 7, 8, 9. That's horizontal flip, right? I'm going to now make a vertical flip. That means 1 would become minus 1 now. It is I that gets changed now. This is 8, 5, 2. Now I equal to minus 1 would come to 1, 7, 4, 1, and 9, 6, 3 would come here. Okay, this is your h of minus I comma minus j. Hope this is clear to you, right? You could notice here when your mask is symmetric, you would get the same one after even flipping your mask. With that, I would now give you a couple of exercises to work out. To simplify these exercises, I'll move to 1D instead of 2D. Later, with a very little amount of effort, you will be able to scale it up and see that the same thing holds for a 2D image as well. Assume that you have 5 pixels here, and let this be the center pixel. Let's assume that initial intensities here are I1, I2, I3, I4, I5. Okay. Now I want to replace the center pixel value with another value I that minimizes an optimization function which I am defining as, let the subscript let me mark it with P. I'm varying it I1 to I5, so let it be P1 to P5, and I want to find out, give it a value I which is equivalent to the sum of squares of the differences across all its neighbors. This is what I would like to compute. Is that clear? So the question for you is, you need to do it analytically here. Compute I such that it minimizes the sum of this. So assume that here I am in fact considering a neighborhood of from minus 2 neighbors on the left and 2 neighbors on the right. Okay, so this is essentially 5 window size W is 5, but again this is in 1D right now. So you compute that, and now you specify the corresponding kernel to do, let's say, correlation. Specify the corresponding kernel. That means I want to specify the corresponding mask for correlation, so that you would get the same operation done when you are going to correlate with that particular mask. Okay, and then can you somehow relate it to any of the examples that we discussed earlier, or something that you already know? So what I would like to take a look at is, what is your inference from this kernel? Okay, this is what I would like you to try out. That's the first exercise for you. Then I have one more exercise. The second exercise is intended to give you some practice with performing convolution and correlation. So let me give you a mask indicated again by H, which is a 3 by 3 mask, as you could see here. Let's assume that it has values of, first row is all ones, second row is 1 2 1, the last row is -1 1. H is given to you. Now image is also given to you. The image, let me denote it with I. Let's take an image of size 4 by 4 here. Let the values be 2 2 2 3, 2 1 3 3, 2 2 1 2, 1 3 2 2. Now you compute correlation of, let's call I1, which is correlation of I with H. Okay, I'm not sure if the notation of correlation, the symbol is correct, but you take it for granted for now. Thus I want you to compute the correlation of I with H, that image, and then I would like you to also compute the convolution of I with H. Again, you would face problems when you are dealing with the boundary pixels. Like for example, you are placing your kernel to compute the value at this first pixel. So when you are placing the center of this at 2, you do not know the values here, right? And of course here also you would require. So what I would say is, use zero padding. So essentially I want this I1 again to be of size 4 by 4, and similarly I2 also will be 4 by 4, and you appropriately use zero padding. I'm sure you all know this zero padding from your DSP course. Okay, these are the two exercises I would like you to do. Okay, that's all for this video lecture. We discussed in this lecture about particularly spatial filtering for image smoothing. We will see different kinds of image enhancements in the coming video lectures. Thanks for watching. See you in the next video lecture. Bye. Take care.